Hi, in this video we're going to look at the third hand rule, which is kind of the most complicated of the three because it's got actually three parts to it, but also probably the most useful to us, the one that we're going to use the most often when we're doing problem solving. It's not to say that the first and second hand rules aren't good and aren't useful to us, but the third hand rule just gets more use out of it for problems even that we do later on in the course. So, important things to remember are, first of all, because we're still, assuming things like electron flow current, we're going to use left hand for that, right hand for anything that's positive. But we're going to see that we have to play off of that a little bit more in this hand rule, because now we're not just going to be doing current in a wire, electron flow with our left hand, we're also going to be doing some stuff eventually with electrons themselves just flying around through the air. And that means that sometimes we will do just like protons or alpha particles with a double positive charge flying through the air, and that's right hand. So right hand, everything that's positive, left hand, everything that's negative. And we're just going to see that we kind of flip back and forth between the hands a little bit more in the third hand rule. Now, in this hand rule, you really want to make sure that you are holding your hand with your thumb and your fingers perpendicular. We never can do something like that because that's going to screw up our answers. But what we're looking for is what the three parts are going to be on our hand, which might sound a little bit weird because, well, I've got a thumb and I've got fingers, so how are we going to get the three parts? Well, first of all, anything to do with either the direction current is flowing in a wire or the direction a charged particle is moving, that's going to be our thumb, okay? Anything to do with the external magnetic field, because even if we have the wire and the wire makes its own magnetic field, I know all that, that's like first hand rule sort of stuff. In the third hand rule, we're going to have an external magnetic field. That's our fingertips. Fingertips point in the direction of the external magnetic field, which could mean pointing north to south. Finally, the big part about what third hand rule is doing is allowing us to predict the direction of the force exerted on the wire or the charge while it's in that external magnetic field. And that's because whether it's a moving charge or a wire, it's going to have its own little mini magnetic field. It interacts with the external magnetic field and gets pushed around because of that. So if you think about it with your hands, if you were going to push something, you would push with your palms, right? So your palm is the direction of the push. Wherever you would push with your palms, that's the direction of the force. So I'm going to show you a basic sort of question that we could do with this. I'm going to draw my external magnetic field like this. Now, please understand, I'm not trying to suggest that I've cut off south and north poles from this. This isn't some sort of monopole trick or something like that. These are still dipoles. It's just that this is the area I care about, so this is the only part that I draw and that I'm concerned with. Okay? Now, that's the external magnetic field. And if I was going to think about where's that external magnetic field pointing, I would say north to south. So even though I haven't done anything else yet in the drawing, with my left hand, because I'm going to do this first example with electron flow current in a wire, okay? I'm going to make sure that I point my fingertips that way, pointing north to south. Now I can still rotate my hand like this, but what I can't do is start changing where my fingertips are pointing, okay? My fingertips are going to be locked so that they're always pointing towards south. So in this magnetic field, I'm going to have a piece of wire, and I tell you that the electron flow current is going up through the wire, okay? Only the section of wire that's actually in the magnetic field gets affected by the magnetic field. So any parts of the wire that are outside, we basically say nothing's happening to them. There might actually be something, but we only focus on what's happening within the external magnetic field. So, in this example, my fingertips, like I said, have to point to south. The current is flowing up that way, so I turn my hand until my thumb is pointing upwards in the direction of the electron flow current. Now I look at where my palm is. my palm, if I was going to start pushing with my palm, I wouldn't go like into the board. That's like pushing with my knuckles out that way. No, I would push with my palm out towards you. That's the direction of the force. So in this diagram, I would draw a circle with a dot, because that represents coming out towards where you are, and I would label it FM, so that it's really clear that what I'm drawing there is the magnetic force. In fact, in the diagram, if they did ask you, hey, what's the direction of the external magnetic field, you could just draw an arrow going across like this. I know there should be a whole bunch of arrows for the whole field, but I don't want to fill this up with too much stuff. So I'm just going to draw one arrow showing that I know the field points north to south, and then I would label it B external for being the external magnetic field. So there is the whole sketch for that one. Now, instead of saying to you, hey, I know what the field is and the current, ask about the force. I could flip it around and I could ask you for something different. For example, I could draw my magnet like that. I'm going to draw the wire like this with electron flow current going that way. And I'm going to tell you that in this example, the wire, the portion that's in the magnetic field, feels a magnetic force into the board. And I want to know which one of these is north and which one is south. Okay, so again, I'm going to use my left hand. Okay, the direction, it doesn't matter which one you start with. I tend to start with the current if I've got it, because I'll get my thumb pointing the right direction. I know that my thumb has to point that way on my left hand, because that's the direction the current is going. Now, the other thing that I know from this is that the force is pushing into the board. So I'm going to rotate my hand until my palm is pushing into the board. I've still got my thumb pointing the right direction. I didn't start turning my hand like this. My thumb is still pointing in the direction of the current, and I'm pushing into the board. I look at where my fingertips are pointing. My fingertips are pointing in the direction of the magnetic field. They're pointing like that. Magnetic fields point north to south. So this is north, and that is south. Okay? So I can give you the current and the direction of the force, and you can tell me the magnetic field. Another example I could do is something that looks like this. Now, I'm going to intentionally draw something a little bit weird here. I'm going to draw the wire like this. And what I really mean is that I've taken the wire and I've just tilted it a little bit, okay? Now, along with all of this, I'm also going to tell you that the direction of the force that it's experiencing is out towards you. FM like that. The question I'm going to ask is, which way is the current? Now, this one is a little bit weird because, well, what am I supposed to do? Like tilt my thumb or something? Okay, what we have to remember is that although it's pointing at an angle, like anything in physics, that basically means that it has components. Well, I know, crazy component stuff. So what I'm going to first do is figure out what direction the current would flow to get this kind of a force in like a perfect situation, and then I'm going to use that to figure out which way it's pointing on this tilted wire. So I'm using my left hand. I'm going to have to turn my hand so that my fingers point to south, okay? My palm is pushing out towards you, the direction of the force. My thumb is pointing up. So that means if I was looking at components of this, the y component would be pointing up, okay? That means the x is going to be going that way, because for this wire, current flowing that way could be explained by an x and a y component. The y component is the part that I figured out is happening, so that overall the current must be going like that. I'm going to kind of simplify this for you. I'll take away some of that stuff. And there's the direction of the current. Okay? I know that the current isn't going perfectly up, but even if there's a component of it going up, there'll be at least a little bit of force that happens because of that. Now in these examples, I'm doing electron flow going through a wire, and I could do conventional current, and I would just switch to using my right hand. But I want to show you what happens if instead I switch to doing things with charges, because there's lots of questions we do with those. And I'm also going to change a little bit about the way that I'm drawing the magnetic field. Because I'm going to draw the magnetic field like this, which you're going to think, well, where is the actual magnet that's making this magnetic field? So this is the external magnetic field. What I want you to imagine is that for this, the magnetic field is pointing away from us into the board. For that to happen, there needs to be like a north pole of a magnet out here, and somewhere on the other side of the board, a south magnet, the south pole of a magnet, because that would make the magnetic field point that way. So when I do this question in a moment, with my left hand, I'm going to have to make sure that my fingers are pointing away from you, pointing into the board, because that's the direction of the magnetic field. What I'm going to do is I'm going to say to you, I have an electron, and I'm shooting it that way. There's no wire, okay? I still get to use my left hand though, because my left hand is anything negative that's happening. And I still do all the stuff the same. It's just that instead of my thumb being the direction of the current in the wire, it becomes the direction that a charged particle is moving. So in this example, I've got to get my hand pointing into the board for the external magnetic field, and then I'm going to turn my hand so my thumb points that way, because that's the direction that the electron is moving as it enters the magnetic field. That means that my palm is pushing down. So the direction of the force exerted on it is pushing down. Now that means that as the electron enters this magnetic field, it's not going to keep going in a straight line. Because it's feeling that force, what I would watch is as it goes through a path, something like that. Now you got to be careful about the question that you're asked, because if the question says, what's the direction of the magnetic force, you'll just say down. But if it asks you to sketch the path that the electron takes, then you want to draw this curved path, because that's a different question. It's saying what happened to the electron because of that force that it's experiencing. Now, I can change this around a bit. Let me just kind of get rid of some of this stuff by just changing the particle that I'm dealing with. So what if, instead of this being an electron, it was something with a positive charge, like an alpha particle, still traveling to the right? Now, as it enters the magnetic field, I would have to use my right hand because it's got a positive charge. My fingers still point into the board because that's the direction of the magnetic field. I turn my hand until my thumb is pointing that way, the direction that the alpha particle is originally traveling, and I find that it's being pushed up by my palm. So FM is acting upwards. That means that if I watch this alpha particle, I would watch it go through a curved path upwards because it's being pushed up while trying to travel that way. This sort of a way of manipulating the direction a charged particle is moving can actually come in really handy for us in later chapters when we want to do some tricks with even potentially using this idea to trap particles in a magnetic field and make them spin in circles for us. In any of these cases though, we're always using the same idea, the same parts of our hands. The charged particle or the direction of the current is our thumbs. The external magnetic field is where our fingers are pointing, and our palms are the push. So I hope that helps you out with the third hand rule. Good luck with that.